Hi friends, in this diode problem, some series of three diodes are connected to use it as a voltage regulator basically. So we need to analyze the circuit for its constant output voltage if there is a change in input voltage, or otherwise if there is a change in load resistance basically. So in the very first part we'll uh, see here it is asking calculate the change delta V naught, a change in output voltage, regulated output voltage basically, caused by plus or minus 10% change in the power supply voltage, that is input voltage. Let's take uh, um, in this clearly V naught, the output voltage it is given as 2.1 volt, and three diodes are connected in series, so 3 times diode voltage, let's say it is a VD. So 3 VD is nothing but 2.1 volts, so each VD is 0.7 volts, and clearly V out it is given 2.1 volts, it is already written there. So now let's calculate the current through the diode. So that is ID is nothing but 10 minus V out over R. R is nothing but 1 kilo ohm, here it is given. So 10 minus 2.1 over 1 kilo ohm. So which is equals to ID is nothing but 7.9 milliamperes. So now let's go for diode small signal equivalent. So each diode will have a small resistance in forward biased direction condition. So that is called incremental resistance. Incremental resistance is nothing but RD is nothing but VT, that is thermal voltage over the current through the diode. So VT it is already given in question itself, that is 25 millivolt at room temperature. So ID is now 7.9 milliamperes. So the incremental resistance RD is nothing but 25 over 7.9. So let's calculate how much it is. 25 over 7.9 is, so it is 3.164. So 3.164 ohm per diode. So basically, so let's say the equivalent circuit of this is like looks like this. This is R, so that is 1 kilo ohm, and this is small r, which is lowercase letter basically. This is R is nothing but 3 times diode incremental resistance. So let's calculate how much it is. 3.164 multiplied 3 is 9.492 ohm basically. So this is 9.492 ohm. So here it is given 10 volt plus or minus 1 volt. So that is basically the input volt is changed by varied by 10%. So let's say this is basically V naught, that is V out, output voltage. So let's calculate the change in output voltage. So let's apply the change in input voltage, which is delta V in. So simply it is a voltage divider circuit. So delta V naught is nothing but 9.492 over 9.492 plus 1000. It is a simple voltage divider circuit, delta V in. So delta V in, if you take plus or minus 1, so this is corresponds to 9.492 over 9.492 plus 1000 is basically 9.4 millivolts. So 0.0094 plus or minus volts. So basically delta V V naught is nothing but 9.4 millivolt plus or minus either of the directions. If the change in input voltage is positive by 1 volt, if the input volt is increased by 1 volt, then output volt is going to increased by only 9.4 millivolt, so which is very less actually. So in this way this circuit can act as a voltage regulator, because the change in input voltage is highly suppressed in output voltage. So similarly, now let's keep the input voltage is constant at 10 volts, but let's add a load resistance of 1 kilo ohm. So in this case what happens exactly, so here it is, R is 1 kilo ohm, it is connected there to the source voltage. So here 3 diodes are basically connected in parallel. So the circuit looks like somewhat like this. So basically we are expecting our voltage at 2.1 volt, but this case we are adding one more load resistance. Earlier in part A we have not added any load, so basically there is no load calculation, but here it is, we are adding some load across the output voltage output. So here the load current IL is nothing but 2.1 over 1 kilo ohm, so which is 2.1 milliampere. But earlier I is equals to IG, that is no load current, that was I think 7.9 milliamperes. So now new ID, new diode current when connected to a load is 7.9 minus 2.1 milliamperes, because by introduction of a load resistance across the output, we are expecting a less current through the diodes, that is IG new is nothing but 5.8 milliamperes, because load is drawing some 2.1 milliamperes of current. So now let's calculate new diode voltage, that is, see, we know the Shackley's current equation, that is ID is equals to IS over e power VD over VT. So now the new current is 5.8 milliamperes, 5.8 milliamperes over, earlier it was 7.9 milliamperes, so which is equals to e power VD. So now the new VD we don't know, and earlier VD was 0.7 volts over VT. So now e to the power VD minus 0.7 over VT is nothing but 5.8 over 7.9. Clearly VD is 0.7 let's take a natural logarithm, so that VD o minus 0.7 over VT is nothing but ln 5.8 over 7.9. So now the new VD is nothing but 0.7 plus VT times ln 5.8 over 7.9. Clearly VT is 25 millivolt is given there. So 0.7, let's take calculator. So 0.7 plus 0.025 natural logarithm 5.8 over 7.9, so which is equals to the final calculation is 0.692 volts. Each diode is having a drop of 0.692 voltage. So V out is nothing but now 3 times Vd, which is 0.692. Again, if you take a calculator, so 3 times 0.692 is nothing but 2.076 volt. So by connecting a 1 kilo ohm of load, your output voltage basically is decreased by 2.076 minus 2.1, which is nothing but minus 2.1. If you check it, basically it is minus 24 millivolt. So your output voltage is varied by very less, which is just at 24 millivolt when connected to a load resistance of 1 kilo ohm. So in this way we can deduce one simple thing, that this circuit can act as a very good voltage regulator, because it is suppressing the changes in input voltage very well. 1 volt, that is 10% change in input voltage, is appearing across the load by just 9.4 millivolt. Approximately it is suppressing the change in input by 100 times. Similarly, if a load resistance of 1 kilo ohm added across the output voltage, decreasing the output voltage by just 24 millivolts. So this can act as a very good voltage regulator. Thank you for watching. Please subscribe my channel.